This video contains audio content only. There are no visual elements or images accompanying the audio. If you're expecting to see video footage, please note that this is an intentional audio-only presentation. We recommend listening to this content rather than watching the screen. Thank you for your understanding and enjoy the audio. Welcome. Have you ever wondered what happens to nuclear waste? Or imagined a battery that could last for thousands of years? In this exploration, we'll delve into the fascinating world of the carbon-14 diamond battery, a groundbreaking technology that promises to revolutionize how we think about energy and waste. We'll break down complex scientific concepts into easy-to-understand language, making this cutting-edge innovation accessible to everyone. Prepare to be amazed as we uncover the story of how nuclear waste, specifically radioactive graphite from nuclear reactors, can be transformed into a clean, long-lasting power source. We'll explore the ingenious process of extracting carbon-14 from this waste and encapsulating it within a diamond to create a battery unlike any other. Think of it: a battery powered by the same element used to date ancient artifacts, now providing sustainable energy for the future. We'll uncover the science behind this remarkable technology, explaining how the natural decay of carbon-14, a process known as beta decay, can generate a continuous flow of electricity. We'll delve into the unique properties of diamonds that make them the perfect material for containing and harnessing this energy. Imagine a diamond, not just a symbol of beauty and luxury, but a powerhouse of sustainable energy, quietly generating power for millennia. Safety is naturally a key concern when discussing anything related to radioactivity. We'll address these concerns head-on, explaining how the carbon-14 diamond battery is designed with multiple layers of protection to ensure its safe operation. We'll also discuss the surprisingly small amount of radioactive material used in each battery, putting any potential risks into perspective. But the story doesn't end there. We'll also explore the potential applications of this revolutionary technology, from powering medical implants to enabling long-duration space missions. Imagine a pacemaker that never needs replacing, or a spacecraft venturing into the depths of the solar system, its instruments powered by a diamond battery for generations to come. The possibilities are truly astounding. Join us as we embark on this journey of discovery, exploring the fascinating intersection of nuclear science, materials science, and sustainable energy. Get ready to learn about a technology that not only solves a waste management problem but also offers a glimpse into a future powered by clean, long-lasting energy. The carbon-14 diamond battery is more than just a scientific curiosity. It's a beacon of hope, a testament to human ingenuity, and a potential game-changer in the quest for a sustainable future. Chapter 1. From Nuclear Waste to Everlasting Power: The Genesis of the Carbon-14 Diamond Battery. Our story begins not with a spark of genius, but with a looming shadow: nuclear waste. The image that often comes to mind is spent nuclear fuel, glowing ominously, demanding specialized storage and constant vigilance for millennia. But there's another form of nuclear waste, less dramatic perhaps, but posing its own unique set of challenges: graphite. These unassuming blocks of carbon, crucial in certain nuclear reactors, hold a hidden secret. They become quietly radioactive, transforming over time into something more than just a moderator of nuclear reactions. In the heart of nuclear fission reactors, where atoms are split to release tremendous energy, graphite plays a crucial role. Its purpose is to control the chain reaction, slowing down the neutrons released during fission to maintain a steady and controlled release of energy. Imagine a bustling city intersection, where graphite acts like the traffic lights, ensuring a smooth flow of neutrons instead of a chaotic pile-up. But this vital role comes at a cost. As the graphite performs its duty, it's bombarded by neutrons, some of which are absorbed by the carbon atoms within the graphite structure. This absorption transforms the stable carbon-12 into its radioactive cousin, carbon-14. Now, carbon-14 is fascinating stuff. It's the same isotope used by archaeologists to date ancient artifacts, revealing secrets of civilizations long past. But in the context of nuclear waste, it presents a significant challenge. The UK, with its history of nuclear power generation using Magnox reactors, which relied heavily on graphite moderators, now faces a mountain of this mildly radioactive material, nearly 95,000 tons of it. That's equivalent to the weight of about 130 fully loaded jumbo jets, all emitting a low but persistent hum of radioactivity. Storing and monitoring this vast quantity of graphite, with its 5,700-year half-life, presents a considerable long-term commitment, both financially and in terms of ensuring public safety. But what if, instead of seeing this radioactive graphite as a burden, we could see it as an opportunity? What if this waste, this byproduct of nuclear energy, could be transformed into something valuable? This is the question that sparked the imagination of researchers at the University of Bristol, leading to a true eureka moment. Professor Tom Scott, a materials scientist at the University of Bristol, along with colleagues from various disciplines, nuclear physicists, chemists, and other material scientists, began to explore this intriguing possibility. They knew that carbon-14, as it decays, emits beta radiation, essentially a stream of high-energy electrons. They also knew that diamonds, being a crystalline form of carbon, possess remarkable properties. Not only are they incredibly hard, capable of withstanding extreme conditions, but they are also excellent semiconductors, meaning they can conduct electricity under certain circumstances. Could these properties be combined to create a battery? The idea began to take shape. A battery powered by the radioactive decay of carbon-14, safely encased within a diamond. But diamonds aren't just hard, they're also incredibly effective at containing the short-range radiation emitted by carbon-14. This led to the concept of a sandwich structure, a core of radioactive carbon-14 diamond, surrounded by a layer of non-radioactive, lab-grown carbon-12 diamond. This outer layer acts as both a shield, preventing any radiation from escaping, and a booster, enhancing the flow of electrons generated by the decaying carbon-14. The initial prototypes used nickel-63, another radioactive isotope, as the radiation source. This allowed the researchers to test the basic concept of a beta-voltaic cell, a device that converts beta radiation into electricity. But the real breakthrough came with the shift to carbon-14, extracted from the very graphite blocks that posed such a waste management problem. This was more than just a scientific curiosity, it was a potential solution to a real-world challenge. Extracting the carbon-14 from the graphite, however, proved to be a significant hurdle. The process involved heating the graphite blocks to extremely high temperatures, turning the carbon into a gas, and then carefully collecting and purifying the carbon-14. This required the development of specialized equipment, including a plasma deposition rig, a sophisticated piece of machinery capable of growing thin layers of diamond under controlled conditions. This rig became the heart of the diamond battery project, allowing the researchers to create the precise diamond structures needed to encapsulate the carbon-14. This development wouldn't have been possible without a collaborative effort. The University of Bristol teamed up with the UK Atomic Energy Authority, UKAEA, bringing together academic ingenuity with the UKAEA's expertise in handling radioactive materials and their deep understanding of fusion energy. The UKAEA's Culham campus, home to cutting-edge fusion research, became the birthplace of the first carbon-14 diamond battery. The knowledge gained from years of fusion research, particularly in handling and containing radioactive isotopes like tritium, proved invaluable in developing the diamond battery technology. The ingenuity of this approach is captured perfectly by the analogy of a cosmic rag and bone man. Just as a rag and bone man collects discarded materials and transforms them into something useful, the carbon-14 diamond battery takes a hazardous waste product and turns it into a valuable resource, a source of clean, long-lasting energy. It's a testament to human ingenuity, finding solutions where others see only problems. The carbon-14 diamond battery isn't just a scientific curiosity, it's a beacon of hope. It holds the potential to solve both energy and waste management challenges, ushering in a new era of sustainable power. Our story has just begun. In the following chapters, we'll delve deeper into the science behind this remarkable technology, exploring its structure, safety, and the myriad potential applications that could revolutionize how we power our world. Chapter 2. A Diamond's Glow. Unlocking the Secrets of Carbon-14's Energy Potential. The heart of the carbon-14 diamond battery lies in the fascinating, yet predictable, decay of a radioactive isotope. Carbon-14, unlike its stable sibling carbon-12, possesses an inherent instability within its nucleus. This instability arises from an imbalance in the number of protons and neutrons, a delicate nuclear dance that nature seeks to rectify. To achieve stability, carbon-14 undergoes a process known as beta decay. Imagine the carbon-14 nucleus as a tightly packed bundle of energy, constantly vibrating with an internal tension. Suddenly, this tension releases as a neutron within the nucleus transforms into a proton, emitting a high-energy electron in the process, known as a beta particle, and an antineutrino, a ghostly particle that barely interacts with matter. This emission is not a mere spark. It's a potent burst of energy, a tiny bullet fired from the nucleus. This transformation doesn't just release energy, it fundamentally alters the atom's identity. With the addition of a proton, the carbon-14 atom, with its 6 protons, now boasts 7, the defining characteristic of nitrogen. Thus, through the act of beta decay, carbon-14 transmutes into its stable neighbor, nitrogen-14, achieving the nuclear equilibrium it craves. This process of decay is not instantaneous, it follows a predictable timeline governed by the concept of half-life. The half-life of carbon-14 is approximately 5,730 years. This means that after 5,730 years, half of a given sample of carbon-14 will have decayed into nitrogen-14. After another 5,730 years, half of the remaining carbon-14 will decay, and so on. This gradual, predictable decay is precisely what makes carbon-14 so valuable in archaeological dating and, crucially, in the diamond battery. It's a clock that ticks for millennia, a slow but steady release of energy that can be harnessed. But how do we capture this energy, these tiny bullets fired from decaying carbon-14 nuclei? This is where the extraordinary properties of diamonds come into play. Diamonds, composed of a tightly bound lattice of carbon atoms, are not only renowned for their hardness and brilliance, but also for their exceptional semiconducting properties and remarkable thermal conductivity. Picture the diamond lattice as a perfectly ordered, three-dimensional grid, each carbon atom firmly locked in place by strong covalent bonds. When a beta particle, ejected from a decaying carbon-14 atom nestled within this lattice, collides with a carbon-12 atom, it transfers its kinetic energy, knocking loose an electron from its orbit. This creates an electron-hole pair, a free electron and the hole it left behind, which acts like a positive charge. This separation of charge is not random. It's influenced by the electric field within the diamond, which is carefully engineered by introducing impurities, a process called doping. These impurities create pathways for the free electrons to flow, generating a small but continuous electric current. Think of it like a pinball machine. The beta particles are the pinballs, the diamond lattice is the playing field, and the impurities are the bumpers, guiding the flow of electrons, the electric current, toward the battery's terminals. This entire process, the conversion of beta radiation into electricity within a diamond, is known as the beta voltaic effect. It's not merely analogous to a solar panel. It operates on a similar principle, converting the energy of particles into electricity. However, instead of photons from sunlight, the diamond battery uses the beta particles emitted by carbon-14. And unlike solar panels which require sunlight to function, the diamond battery generates power continuously, day and night, for thousands of years. The power output of a single carbon-14 diamond battery is measured in microwatts, a tiny fraction of the power consumed by everyday devices. A single gram of carbon-14 produces about 15 joules of energy per day, roughly equivalent to the energy stored in a grain of rice. However, this seemingly insignificant output, coupled with its incredibly long lifespan, makes the diamond battery ideal for applications where low but continuous power is crucial. Imagine a pacemaker, steadily regulating a heartbeat for decades without needing replacement. Envision a sensor, diligently monitoring conditions in a remote or hazardous environment, transmitting data reliably for years on end. Picture a spacecraft, venturing into the depths of space, its instruments powered by a diamond battery, sending back data for millennia. These are just a few examples of how the carbon-14 diamond battery, with its low but continuous power output, can revolutionize various fields, from medicine to space exploration. It's not about brute force. It's about endurance, a quiet revolution in how we power the future. Chapter 3. The Heart of the Matter. How a radioactive diamond can power the future. Let's delve into the intricate structure of this revolutionary battery, exploring how these radioactive diamonds are created and assembled to form a functional power source. The creation of a carbon-14 diamond battery begins with a specialized piece of equipment called a plasma deposition rig. This isn't something you'd find in your average garage. It's a sophisticated apparatus used to grow thin films of diamond under precisely controlled conditions. Think of it as a high-tech oven, where the ingredients are not flour and sugar, but carbon-14 in gaseous form and a carefully chosen substrate, the foundation upon which the diamond will grow. Inside the plasma deposition rig, a mixture of gases, including methane containing the radioactive carbon-14, is heated to extremely high temperatures, creating a plasma, a superheated state of matter where electrons are stripped from their atoms. This plasma is then directed onto the substrate, where the carbon atoms begin to deposit, layer by atomic layer, forming a thin film of diamond. This process, known as chemical vapor deposition, allows for precise control over the diamond's growth, ensuring the uniform distribution of carbon-14 within the diamond lattice. Interestingly, this technology has its roots in fusion energy research. The UK Atomic Energy Authority, UKAEA, a key partner in the Diamond Battery Project, has extensive experience in handling radioactive materials and developing advanced materials for fusion reactors. This expertise proved invaluable in adapting the plasma deposition process for the creation of carbon-14 diamonds. It's a remarkable example of how scientific advancements in one field can lead to unexpected breakthroughs in another, highlighting the interconnectedness of scientific discovery. The prototype carbon-14 diamond batteries are remarkably small, measuring just 10 mm by 10 mm, with a thickness of up to half a millimeter. To visualize this, imagine a square about the size of your fingernail, incredibly thin yet capable of generating power for thousands of years. These miniature power generators aren't just single diamonds. They consist of multiple layers, carefully engineered to maximize efficiency and safety. At the heart of the battery lies the radioactive diamond core, the source of the beta particles that drive the energy generation. This core is surrounded by a layer of non-radioactive, lab-grown diamond made from regular carbon-12. This outer layer serves two crucial purposes. First, it acts as a containment shield, preventing the short-range beta radiation from escaping. This ensures the safety of the battery, making it suitable for use in various applications, including medical implants. Second, the outer diamond layer enhances the battery's efficiency by acting as both a semiconductor and a heatsink. The diamond's unique crystalline structure helps to amplify the current generated by the beta decay, while its exceptional thermal conductivity efficiently dissipates any excess heat. But the diamond layers alone don't make a complete battery. To manage and distribute the power generated by the diamond, two essential components come into play: an integrated circuit and a supercapacitor. The integrated circuit acts as the battery's brain, regulating the flow of electrons and ensuring a stable output. Think of it as the traffic controller, directing the flow of electricity to where it's needed. The supercapacitor, on the other hand, is like a tiny reservoir, collecting the small but continuous trickle of electricity generated by the diamond. Unlike conventional capacitors, which store energy in an electric field between two plates, supercapacitors store energy electrostatically by accumulating ions on the surface of a porous material. This allows them to store significantly more energy than traditional capacitors, while also being able to charge and discharge much faster than batteries. Imagine a dripping faucet. Each drop represents the tiny amount of electricity generated by the diamond. The supercapacitor collects these drops, storing the energy until a sufficient amount has accumulated. Then, when needed, the supercapacitor releases this stored energy in a more usable burst, like opening a valve and releasing a controlled flow of water. This makes the diamond battery ideal for powering devices that require intermittent bursts of energy, such as sensors or small electronic devices. To further illustrate the battery's low power output, consider a typical pacemaker. These life-saving devices operate on just a few microwatts of power, enough to regulate a heartbeat but not much more. A single carbon-14 diamond battery can comfortably provide this level of power for thousands of years, eliminating the need for risky and invasive replacement surgeries. The diamond battery's durability and resilience have been tested in some of the most extreme environments on Earth. In one instance, prototype diamond batteries were used to power sensors inside a remote monitoring station placed on the rim of a volcano. These dragon eggs, as they were called, were designed to withstand the harsh conditions of an active volcano, collecting data on humidity, vibrations, and toxic gas emissions. The diamond batteries performed flawlessly, demonstrating their potential for use in challenging environments, from the depths of the ocean to the vast expanse of space. The carbon-14 diamond battery is not just a technological marvel, it's a symbol of sustainable innovation. By repurposing nuclear waste into a valuable energy source, it offers a glimpse into a future where clean energy and responsible waste management go hand in hand. Chapter 4. The Safety Dance: Navigating the Radioactive Reality of Carbon-14 Power. Now, let's address the elephant in the room: radioactivity. The word itself can evoke images of glowing green waste and ominous danger signs. So, how can a battery powered by radioactive decay be safe? The answer lies in understanding the nature of the radiation involved, the protective measures built into the battery's design, and the incredibly small amount of radioactive material used. The carbon-14 in the diamond battery emits beta radiation, a type of ionizing radiation consisting of high-energy electrons. These beta particles, unlike other forms of radiation like gamma rays, have a very limited range. In air, they can travel only a few centimeters. And any solid material, even a thin sheet of paper, can effectively stop them. Now, imagine the diamond itself. It's not just the hardest known material, it's also incredibly dense, forming a tightly packed lattice of carbon atoms. This dense structure acts as an exceptional shield, effectively containing the beta radiation emitted by the carbon-14 within. Think of it as a fortress, its walls impenetrable to the beta particles trying to escape. The diamond battery incorporates a double layer of protection. The inner core, containing the carbon-14, is encased within an outer layer of non-radioactive, lab-grown diamond. This outer layer provides an additional barrier, further minimizing any potential for radiation leakage. In fact, the amount of radiation that escapes the outer casing of the battery is incredibly small. To put it in perspective, it's less than the radiation you'd receive from eating a banana, which naturally contains small amounts of radioactive potassium. You're also exposed to more radiation from a smoke detector, which typically contains americium-241, an alpha emitter. Furthermore, the quantity of carbon-14 in each battery is minuscule. Remember, the prototype batteries are tiny, just 10 mm by 10 mm by 0.5 mm. The amount of carbon-14 used in each of these tiny powerhouses is far less than what you'd find in a banana, let alone the large graphite blocks from which it's extracted. This significantly reduces any potential risk associated with the battery. Safety is also paramount during the manufacturing process. To prevent any misuse of the radioactive materials, a technique called ion implantation is employed. This process locks the carbon-14 atoms within the diamond lattice, ensuring they can only be used for power generation and cannot be easily extracted or repurposed for nefarious activities. Even in the unlikely event of damage to the battery, the solid form of the carbon-14 prevents it from being easily ingested or absorbed. This is a crucial safety advantage compared to other forms of radioactive waste, like the graphite blocks themselves, which can release radioactive dust particles if damaged. With the diamond battery, the carbon-14 is securely trapped within the diamond's crystalline structure. Disposal of the battery is also carefully considered. Instead of ending up in a landfill or requiring specialized storage, the diamond battery can be returned to the manufacturer for safe recycling. The carbon-14 can be extracted and reused, minimizing the long-term environmental impact. The diamond battery's robustness and safety have been put to the test in extreme conditions. Prototype batteries were even used to power sensors inside monitoring stations placed on active volcanoes. These dragon eggs, as they were called, faced intense heat, pressure, and corrosive gases, yet the diamond batteries continued to function reliably, proving their resilience in extreme environments. This anecdote not only showcases the battery's durability but also underscores its inherent safety, even under duress. The carbon-14 diamond battery represents a remarkable convergence of scientific ingenuity and a commitment to safety. By addressing public concerns about radiation and implementing robust safety measures, this technology offers a sustainable and responsible approach to energy generation, turning a waste product into a valuable resource. The carbon-14 diamond battery presents a revolutionary approach to both energy generation and nuclear waste management. By extracting carbon-14 from radioactive graphite, a byproduct of nuclear reactors, and encapsulating it within a diamond, scientists have created a battery with the potential to last for thousands of years. This innovative technology harnesses the energy released from the natural decay of carbon-14, a process known as beta decay, to generate a continuous, albeit low-level, flow of electricity. The diamond's exceptional hardness and thermal conductivity make it an ideal material for containing the radiation and enhancing the battery's performance. This breakthrough has far-reaching implications. Imagine self-powered medical implants that never need replacing, sensors operating reliably in remote and hazardous environments for decades, or spacecraft exploring the vast expanse of space for millennia, all powered by these tiny, long-lasting batteries. Beyond these specific applications, the development of this technology signifies a shift in how we think about energy and waste. It highlights the potential to transform hazardous waste products into valuable resources, paving the way for a more sustainable and circular economy. This innovative approach to battery design could inspire further research into alternative energy sources and waste management solutions, potentially leading to breakthroughs in other fields. Looking ahead, this research could spark a new wave of innovation in long-lasting power sources for a variety of applications. Further development could focus on increasing the power output of these batteries, potentially by combining multiple units or exploring different radioactive isotopes. The ability to harness the energy from nuclear waste could significantly reduce the burden of long-term storage and contribute to a cleaner, safer environment. The potential applications are vast, ranging from powering remote sensors and medical devices to providing sustainable energy for space exploration and even everyday electronics. What are your thoughts on this groundbreaking technology? Do you see other potential applications for the carbon-14 diamond battery? Share your ideas and questions in the comments below. We'd love to hear your perspective. Don't forget to like this video and subscribe to our channel for more explorations into the fascinating world of science and technology. Suggest topics you'd like us to cover in future videos. We're always looking for new avenues to explore. Remember, the pursuit of knowledge and the spark of curiosity are what drive innovation and shape our future.